Light and light-based techniques for paint evidence analysis. So let's talk about light for just a second before we talk into these other types of analysis techniques, analytical techniques, and before we start talking about glass. So light, you know what light is. It's the what illuminates our world. You can treat it from a physics standpoint as either traveling as a particle or traveling as a wave. This is something that was fairly early established in like early 20th century physics. You can observe light doing things in the world, but you can either design your experiment to look at how light travels through space as if it was a particle or as if it was a wave, and never the same thing twice or at the same time. What's awesome is very recently we actually were able to do that. And there's a really complicated technique. I'll post it on Blackboard if you're interested in looking through this very short article that shows you how it was done. But this is a schematic of light being depicted both as a particle, or that reflects its particle nature, and as wave. Light moves through a vacuum at a constant speed of about 300 million meters per second. It will slow down when it goes through literally anything else. A vacuum is a space that's completely devoid of all other matter. If it goes through air or even the thinnest layers of our atmosphere, it's going to slow down. When light slows down, it refracts. We'll talk about that in a bit. Light, when it encounters an object, can either bounce off of it or pass through it. Depending on the shape of the thing you're working with, it might do both. It depends on the nature of the object as to what exactly light's going to do. Light can be reflected, in which case it's going to be reflected uniformly. If you beam a white light at a surface, it's going to reflect back a white beam in return, provided there's no other obscuring characteristics of the surface. And it'll bend, it'll refract when it goes through transparent or translucent objects. So if light can go through something, it's necessarily slowing down when it encounters that other thing, or at least it's changing its speed based on the other thing it's going through. And when it does that, the light will bend and refract. We can only see a very small range of the electromagnetic spectrum, and that's what we refer to as visible light. So here is visible light that we can see. And if this represents the full range of wavelengths that you can have, you can see this only represents a small amount of it. Different types of electromagnetic energy will travel with different wavelengths. The different types of light are distinguishable by their wavelengths. So electromagnetic energy with very, very long wavelengths, where there's a lot of distance between peaks. Oops. I don't know why that keeps disappearing. I'm sorry. Distance equals wavelength. So if you have a lot of distance between those, it's something like TV or radio signals. There's not much energy behind that. The frequency of those is pretty low. The less space you have between wavelengths, the higher the energy. So you can see based on this schematic, TV and radio waves are very, very low energy and have very, very long wavelengths. Microwave technology has pretty low, slow wavelengths and isn't terribly energetic. We can focus them in our microwave ovens, like from a couple different angles, to create enough heat to cook our food. But a microwave signal in and of itself is not terribly powerful. This just reminds me, if you Google it, I can't assign this for lab because it's a fire hazard, but if you Google it, there's a way of using like a glass baking tray filled with marshmallow peeps in the microwave, and you can see that microwaves are in fact waves. You should look that up on YouTube. It's awesome. Anyway, increase or decrease the distance between the peaks of your waves, decreasing the wavelength, increasing the energy, increasing the frequency. You get things like infrared, which is what your remote works on. Visible light is somewhere in the middle. This is what we see. UV radiation, these things, just think all these things are damaging things. So they must be high energy, therefore high frequency, less space between wavelength type of energy. UV radiation gives you sunburn, gives you cancer, high energy stuff. X-rays are even more high energy. It's this high amount of energy that can break chemical bonds in your body that can give you cancer if you're exposed to them over a certain amount. And even more so, like you can get into radioactive wavelengths, like with gamma rays. Laser is an acronym for light amplification by the stimulated emission of radiation. And what's fun about laser technology is it's actually all of the different wavelengths of light that are being emitted by one little device in a very, very, very focused beam. The stuff that we buy is like super low energy, low intensity. You can get really high intensity lasers to like drill holes in diamonds and stuff. Importantly, the color that you see represents the wavelengths of light that are reflected off of something. So when you see a nice green leaf, you have all your different Roy G. Biv wavelengths of light. What this means is that green light, as it enters, reflects off. Some yellow will also reflect. Some blue will also reflect. But stuff like red actually gets absorbed. Orange gets absorbed. Purple gets absorbed. The things that are absorbed are the colors you don't see. The things that are reflected are the things that you see. You might reflect the different wavelengths of light back at different intensities, and so you can have a skewing of these colors a little bit. But the overall principle is that some colors are reflected back. That's the color that you see. Everything that reflects back is going to have a characteristic wavelength associated with it. So chlorophyll, for example, in that leaf, reflects back green light to your eye at a specific known set of wavelengths. This is a documented thing. We're going to exploit this to characterize different types of paint evidence. So absorptive spectroscopy is where you're going to blast paint of a given color with light. Some of the light's going to be reflected and some of it's going to be absorbed. What this technique will do is it will characterize which wavelengths of light will be absorbed. So it's going to see what's going to be reflected back and it's going to extrapolate what's absorbed in turn. And it can take that and plot it on a graph. It's like the quick and dirty explanation here. You can plot it on a graph. Exactly how this looks will be more or less very, very, very close to unique to whatever substance is in it that's creating the color. So, for example, like this is the red paint off of a ship's hull. It was painted with paint from one manufacturer at one point in time. And this over here is a different paint sample that looked to be, to our eyes, the same as the ship's hull paint. But you can look that there's some subtle differences that maybe make you think that they might actually be different paints. Different type of technology, Fourier transform infrared spectrometry, is where you take that paint sample or whatever colored thing that you're looking at and you expose it to infrared light. This isn't visible light, but it still acts the same way. Some of it's going to be absorbed and some of it's going to be reflected. The absorbed wavelengths will warm up that surface, and you can characterize those wavelengths and display those on a similar looking graph. Finally, a very, very sophisticated and precise method is pyrolysis gas chromatography. So far, I'd like to point out the first two techniques don't necessarily destroy the sample. This does, but you need a minuscule amount of sample to make this work. So you can usually afford to do it if you have access to the technology. So then the paint sample is isolated and it's put into this chamber called a pyrolyzer. a special carrier gas is going to be pushed into that chamber, and it's going to be blasted to anywhere between 500 to 1,000 degrees Celsius, depending on what you think is in there. That's going to basically burn and vaporize all the different constituents of the paint sample that you put in there. And then as one sort of new mixture of gases, that's going to be pulled down through a special column and then detected by a computer. The different types of pigment molecules in that minuscule sample can all be plotted out, just like we saw before, on what's called a pyrogram. Again, this is going to destroy your evidence, but you require so little of it, I mean a really tiny fleck of it, to make this effective, that it's a very worthwhile pursuit to do. And this right here is just a picture of what one of those machines looks like.